I would like now to come back to an example that we let you do in the exercises, and we ask you a lot of questions about it. Trick questions, obviously, and I want to clarify now what's going on in this example and why it's an important example. So what you see plotted here is a convergence plot of Monte Carlo, and I use Monte Carlo to compute the volume of the unit sphere, which means I use uniform samples on the d-dimensional unit cube. I inscribe into this unit cube a part of the unit ball, and the uniform sample, I decide whether that sample is inside the ball or outside the ball, and the ratio of the points inside the ball divided by the total number has something to do with the volume of the unit sphere, obviously. Yeah, so it's the same experiment in computing the value of pi approximately using Monte Carlo law, only in higher dimensions. And what you see here is on the x-axis logarithmically the number of samples. So it starts at 1 million, goes to 100 million. And here you see the error also logarithmically, such that in this double log diagram you see a convergence rate as a straight line, and this one is the line for convergence rate 1/2, the one we expect for Monte Carlo. And then I show you the result here in red, the error for 10 dimensions. And if I look at this error, it looks actually good. So it starts off at 1 million points at around 10 to the minus 4. It seems to converge more or less with convergence order 1/2. And it ends up at being roughly 10 to the minus 6 at 100 million samples, which seems fine. Then I look at d equals 20. That's the magenta line down here. Well, what I first notice is that it's far lower. So at 1 million points, it starts just above 10 to the minus 8. But then it doesn't do a lot, right? It seems to be completely flat. It has very few kinks, and it essentially ends up at the same value when I use 100 million points, which is still something times 10 to the minus 8. So that curve already looks a little bit weird because it doesn't seem to have the stochasticity that Monte Carlo typically has. It's pretty much flat or straight for a large portion of the time. And then, well, what we do in these other lines here, we look at the relative error. So up here, this is the relative error of the 10-dimensional case. And well, it has the same similar behavior than the absolute error, only it's a little bit larger. So it starts off at 10 to the minus 2 and finishes at 10 to the minus 3, meaning I get 3 digits of the result correct, which, well, it's kind of okay. It's not what we expected when we have a 10 to the minus 6 error, but well, that's the case. But now if I look at the 20-dimensional results, something stunning happens. Actually, this error is on the order of 1. It's actually even bigger than 1 at 10 million points and stays at order 1 here, which means the result computed by Monte Carlo is completely useless. It essentially tells you the volume of the unit sphere is roughly 0, but you knew that before. Yeah, so measured in sense of the relative error, the information content here, the Monte Carlo method with 100 million samples, lots of samples, for a very simple example, namely just computing the volume of the unit sphere, is completely useless. So let me write this down. So in an exercise, we have investigated the convergence of the MC method. When approximating the volume of the unit sphere, which, by the way, you can compute on paper of the units. Well, it involves a gamma function, but so using uniform samples in every direction or in every dimension, it can be seen that while the absolute error looks fine, with n equals 10 to the 8 and d equals 20, the MC result gets no significant digit. Of the result right, yeah? So that's the relative error. Well, that's not great with 100 million samples. And what's going on here? So let me discuss this using an example or a model. We take any set, which is a subset of the unit cube, yeah? So that can be the unit ball, something like this. And we look at the characteristic function on that set. But, so I write it like this. So this is the function that's 1 on the set and 0 outside of the set. But I make it such that this function integrates to 1. So let me write this down. So the characteristic function of that set is 1 if z is in A, 0 if z is not in A. And we use this notation, that's the volume of A. And by construction, that function integrates to 1. So that means the relative error is the absolute error. Or the absolute error is the relative error. Yeah, that's why I constructed it like this. That's why I divided by the volume. Yeah. It's the characteristic function, but in such a way that it integrates to 1. And let me write down this phrase so that absolute and relative error are the same. The same. Okay, and then, well, we can look at the Monte Carlo error. So we can, which is a formula for the absolute error. Is this one. So epsilon root mean squared. Square is the expected value of QG minus QN bar G. You know this. And it's the variance of the function divided by n. And well, now we need to compute the variance. And here, what's V of G? Well, you can look into the definition, yeah? Integral over the unit cube G of Z minus the true integral squared dz, and well, by construction we know that the true integral is equal to 1, so this is just the integral over the unit cube of G of Z minus 1 squared dz. Looks very simple. And now, well, this I split. I know G of Z takes on 2 values. It takes the value 1 over A on A and 0 outside of A. So I could split the integral into the integral over A. I know that G is actually this on that set plus unit cube without A, and the function value is 0 there. Yeah, so that's actually the integral. The function takes on 2 values only. And well, now I'm integrating constants, yeah, so the first integral is just this squared, and the second one is then 1 minus A, that's the side of the set, times 1. And well, I need to just do very, very simple algebra now. That's 1 over A squared minus 2 over A plus 1 minus A. And well, what do I see here? That well, let me do another step. So that's 1 over A. Let's do it on the other page. That's actually 1 over A minus 2 plus A plus 1 minus A. So I see that this and this together cancel. And this and this together give you a -1. So the result is that this is 1 over volume of A minus 1. And well, what happens in the unit sphere in the case of the unit sphere? Well, no, so now this was a simple enough calculation. Yeah, so this is my model. So in the case of the unit sphere, my characteristic function, the trick is that the unit spheres get really, really small. So the volume of the unit sphere goes to 0 as d goes to infinity, actually faster than exponentially. Namely, the volume of the unit sphere is pi d over 2 gamma d plus 1/2. It's the gamma function, and the gamma function is an approximation of the factorial, or the generalization of the factorial. So that's d minus 1/2, d minus 3/2, and so on, up until 1/2 pi 1/2. And that goes to 0 really, really, really fast. Well, that explains why in this example Monte Carlo is so bad, because in fact, in the Monte Carlo error estimate, the n is fine, but the variance in this error estimate actually explodes completely in this case. Yeah, so I have a very small set, the characteristic function becomes really, really peaked on that set. Yeah, so the picture in 1D would look like this. I have the interval 0, 1. I have the set A here, which is this one, and then it needs to be done such that this is integral 1, so this one here is 1 over A. So if A gets smaller and smaller and smaller, this becomes a tall peak, which goes higher and higher and higher. Yeah, so if I make A smaller, this one goes higher. And the same happens with the unit sphere. The set gets smaller, the peak gets higher, and with that, the variance gets higher. All right, and I have an even simpler example. Why? Now you might say, well, that's unfair, the unit sphere. But I can give you an even more stunning example. I take a set which is itself a hyperrectangle. Zi minus delta 2, Zi plus delta over 2, let's say the BA cube with side length delta and center, which is Z. Well, so for this we can say something. So since the volume of A is just equal to delta to the power D, we get that the variance of the characteristic function of G is simply 1 over delta to the power D minus 1. So I have something that depends exponentially on the dimension again. And even if you feel like you're taking all of the unit cube already, so I'm taking the center of the unit cube and delta 0.999, so I feel like I'm taking 99.9% of the cube in every dimension. That still goes to infinity, this expression with increasing d. Var g tends to infinity exponentially with d. Yeah, so this picture here that you have in mind, I take 99.9%. It feels like here, this gets almost to the boundary, even if it's like this. So in every dimension, that's 99.9%. Still integrating this thing with Monte Carlo in high dimensions doesn't work. Yeah. ultimately. So let me finish this and then give you the reason. So if Yg is roughly 1 over delta to the power d, just throwing away the minus 1, then according to our definition of the curse of dimensionality, epsilon squared is roughly 1 over n times 1 over delta to the power d, right? By the Monte Carlo error formula. And in order to reach an accuracy of epsilon, and we need to take n roughly 1 over delta to the power d times 1 over epsilon squared. And according to our definition, Monte Carlo suffers from the curse of dimensionality. Our definition, Monte Carlo doesn't work here, and if it doesn't work, suffers from the curse of dimensionality. So why is that the case? Well, there is a saying that in high dimensions, the volume lies in the corners. Actually, so I'm missing the corners here. And actually, in high dimensions, that's in the corners. A better picture that you often see is this one here. Imagine I have now the unit cube, and inscribed in this is the unit sphere. So what you see here, the distance to the top corner, yeah, so the red line, that's always square root of d by Pythagoras. And that distance here in the unit sphere is always 1. So in fact, in high dimensions, the stuff that's here is square root of d minus 1. So that really gets long. So the saying really is the volume is in the corners here, because that distance really gets big in high dimensions. Although from the 2-dimensional and the 3-dimensional picture, you feel that's not the case, but it's actually the case. And so why doesn't Monte Carlo work? Yeah, so we see this in the error estimates. You can think about it as in one more way. The unit sphere is really small. This set here in high dimensions is really small. So Monte Carlo has a hard time ultimately of putting a sample into that set if that set is exponentially small. And that explains, coming back to here, the weird behavior of Monte Carlo in this case. There is actually, for a long time, between 1 million points and 10 million, almost 10 million points, there is no point that enters the unit sphere in 20 dimensions. All of my samples are outside. Then I see one, which is inside. And then for a long time, so here I maybe see another one and another one and another one, but I can almost count how many of those samples land actually inside the unit sphere. And all of the other ones, hundreds, so not 100 million, but almost 100 million are outside, actually, because it's so small. And so that's what I want to write down in a remark. So this behavior can also be understood as a Bernoulli experiment. Also, if we think of Monte Carlo as a Bernoulli experiment, with success probability P, which here is really small. And when we repeat this experiment, we get on average 1 over P successes, or no, we need on average 1 over P trials to have 1 success. Yeah, so 1 point inside the unit sphere. And in high dimensions, P, that success probability, might behave exponentially badly. 2 to the minus D. And in that case, if that's the case, so it's the case for the unit sphere or with any other of these sets, looking at the relative error, the Monte Carlo method must suffer from the curse of dimensionality. All right, so what I want to tell you is that when you hear the phrase Monte Carlo does not suffer from the curse of dimensionality in the literature, that does not mean that Monte Carlo is a good method in high dimensions. Yeah, it works, but the result it may give you has no guarantee of being accurate if I apply Monte Carlo in high dimensions.